think I'll stand instead. It's good to see you all. All right, so let's talk about some advanced async and possibly some egg boiling. For those of you that have read my book, I talk about how you can optimize boiling your eggs. So I'm going to go into the compiler stuff, what happens when we apply async and await in our C# applications, and why it might be important to understand what really happens behind the scenes to avoid things like deadlocking and swallowed exceptions. So I'm Filip Ekberg. I'm a C# MVP, and I recently moved here from Sweden to work at Redify as a senior developer. And if you have any questions about async, C# or how to build IKEA furniture, you can ping me on Twitter or just send me an email. Okay, don't ask about IKEA. So about a year ago, I published this book here. It covers a vast variety of different technologies, patterns, and practices using C#. And one of the chapters actually covers the basics of async. And if you don't know anything about async, I advise you to buy the book, even if you do know anything about async. So I'm going to talk about the advanced parts of async and what happens behind the scenes. So you should be fairly familiar to what happens in this code sample. Basically, I have a class here that has two methods, where one of them is an asynchronous method. So it's simply marked as async. We have an awaiter inside the method, and we return a constant value. So I'm not expecting you to understand what happens when the state machine executes this, but I expect you to understand that this method is actually going to be coming back to the return statement when the task for ball X is completed. So let's actually talk about what happens here behind the scenes. This method here is marked as async. We have a simple task returned from this method, and we have an await inside the method. If we just step away from the body for a second and talk about the await keyword. So what actually happens when we mark our method as async is that it's going to take the entire body of the method and shove that into a state machine. So no matter if we use the await keyword or not, the code is going to be transformed and put inside a state machine. And that's quite significant. So when we apply the await keyword, what actually happens inside the state machine is that it's going to trigger a callback to the same method body once more when the task that it's awaiting for is actually completed. So when the compiler compiles this, it generates a structure that implements an interface called Async state machine. And the Async state machine has a method called MoveNext and another method called setStateMachine. The MoveNext method is the method that handles the state inside the state machine and helps us do all the crazy stuff with the async method. So here's a complete sample of the structure that is generated by the compiler. We can see here that we have a reference to the egg boiler class, which is the class that our bool X async lives in. And then we have the amount of eggs here, also in the structure. So it copies the value from the parameter here and puts that inside the structure to use inside the state machine. And then, of course, we have the implementation of MoveNext and setStateMachine. We also have a reference to the awaiter, and we have a reference to something called the async task method builder. We're going to come back to the method builder in just a second. What also happens is that the entire method is going to be rewritten into something that looks like this. So this is the structure that the compiler generated. It's going to initialize that inside the method. It's going to add the reference to the class itself. It's going to set the amount of eggs in the state machine. And then it's going to create a new instance of the async task method builder. And this async task method builder is going to be used to initialize and start the state machine. And it's going to be used to actually track the task that runs inside the state machine. Or rather, the task that executes the state machine. And then we start this builder here. We tell it to start the state machine and sends a reference to the struct that corresponds to our state machine. So let's talk about what happens inside the state machine. So I've taken out a couple of code samples here. The first thing that's important to notice here is that we actually execute the method boolX inside our state machine. And we send a reference to the amount of eggs that we have inside our structure. And then we know that this is going to return a task, so we ask for the awaiter on the task. And the first thing that happens after that is that we check if the task is already completed. Because if it's completed, then we know that we don't have to schedule a callback to this method. However, if it's not completed, then we need to tell the scheduler inside the CLR and inside .NET that we need to call back to this method whenever the task has completed. So we have that waiter here that we're waiting for. We know that this is the task that is currently running. It's not completed. So we simply tell the builder that we have to schedule a callback. And what happens is that it sends a reference to the state machine. It tells it to execute the MoveNext method once more when the task actually completes. So it sort of adds itself to the task's continuation block. And then something else interesting happens here. So we have a return statement that returns from the state machine. This is to let the CPU work on something else. So we don't block the thread or such, so we can continue working on something else. And then the next time we come back here, it's going to jump over this block here and go down and get the awaiter's results by doing awaiter.getResults. And then it's going to set the result on the builder. And what the builder does with the result is that it simply notifies the task that is completed and tells the system that, hey, this task is completed. You have a value for this, or it's no value returns at all. And this is a bit hard to read for you in the back. I can show you this in Reflector later on. But this is the complete decompiled version of MoveNext. And simply, if I actually bring it up instead in Reflector, you're going to see that it's here. Here's MoveNext. Is that better?
Font size.
All right. Appearance.
Yeah. Look at that. Service with smart. Thanks, Darren.
All right. So the first thing that we have inside the MoveNext method is that we have a try-catch block. And this is significant for later on. And then we have a switch statement, which simply corresponds as a jump table to whatever we want to do now in the state machine. So it has a case here for -3, which is just a fault case. Let's call it that. And then there's 1 and 2, 0 and 1. And then we have the default case. So the default case is what we currently just set. Wait for a second. All right. So this is the default case. We just looked at that. So the first time we come into the state machine, what happens is that it's going to come down here to the default case in the jump table, and it's going to get the awaiter. It's going to trigger itself for a callback to the MoveNext method, and then exit the state machine. And the next time we come into the MoveNext method, we're going to be up here in the start of the method, of course. It's going to go into the switch statement, and notice that the state is now 0, so it's going to break from the state machine, from the switch, sorry, and then come down here. So what happens here is that we simply get the result from the awaiter. We have the builder.set result as we saw in the previous example as well. So in this case, we have no return value. You're free to grab pizza if you want. It's okay. Go on.
Don't be shy.
All right, so in this case, we had no return value. The method indicates that because we simply return a task. And this is going to use the non-generic version of async task method builder, which has a method called setResult. And setResult will internally notify the task that it's completed and that there's no exceptions. That's all good. And it's called from within the state machine like this. However, if we have a return value on our tasks, so in this case, we return an integer from our code here, and then we have the constant value of 10 down here that's returned later on. Remember that I said before that the entire body of the method is moved into the state machine. So what actually happens here is that this return value is going to be returned from within the state machine, which is why it's going to be a part of this task here. So the task that we can track from the asynchronous method is going to be the state machine. And the return value that we get from the task is set from within the state machine. And this will use the generic version of async task method builder, which has a slightly different setResult method. So this one here actually expects us to get a result from within the state machine. So what happens is that it comes in here, it tries to set the result on the task, which simply sets the task to, we're completed, we have a result, let's move on. And this is a code snippet from within the state machine. So what happened here is that we call awaiter.getResult, which corresponds to this line here. So when that's finished, we still have to call awaiter.getResult, but then we have the constant value of 10 here. And that's taken from here and moved over here. And then we call the builder.setResult method with the value of 10. And then it's going to call the task and tell it to set the value on the task. And then we can retrieve that value by doing task.result. Something interesting here, though, is if this method here actually would return a value and have a signature somewhat like this. So let's say that boil eggs here would have returned an integer or task of int. Then the awaiter.getResult here would actually give us t. So let's take a look at this example here instead. We create a new egg boiler. We show a message box with a string formatted with eggs and then some value. The value is something that we're waiting for. So what happens here is that the compiler is going to transform this and move everything into the state machine. It's going to trigger a callback. So it's going to execute this first, trigger a callback to actually do this after. So while we write this, it might look like we do the message box first, we pass a value. But what actually happens is that it's going to call that asynchronous method first, and it's going to do some magic here. So this is what the compiled version looks like. It stores the value string here, which has eggs, and then stores that in a temporary variable. It sets the state to 0, which defines that it's completed the next time it's coming back from the callback. We schedule the callback by using await unsafe on completed. We have a reference to the awaiter and to the state machine itself. We simply return from the state machine, and then when that task is completed, we're back to the top and jump down to AC here. And now you see here, awaiter.getResult is inserted into the variable introduced 6. So the compiler introduces a new temporary variable for us, and it simply gets the result from the awaiter here. So this method returns an integer, which is stored here. And then we have the message box down here. So the compiler did a lot of magic here. It moved around a lot of our code. It did a lot of heavy lifting for us. And by seeing all this here up here, that it's so easy to actually write this asynchronous code, you get an idea of what really happens behind the scenes here. So let's talk about PPP, which is Pokemon Programming Principle. So we create an egg boiler here. We're going to catch them all. We're going to catch all the exceptions inside this block here. However, there's a problem here. Our asynchronous method is marked as async void. So remember that when an asynchronous method returns a task, that's the task that runs the state machine. And when it returns void, there's no way for us to actually track the state machine and what's the state machine doing. So don't do this. Because what happens is that it's going to throw the exception on the caller, because there's no way to actually set the exception within the task that the state machine corresponds to. So it's just going to throw it back, and your application is going to crash. So instead, the way of working with async and void is sort of don't do it. So we need a way to track what happens here. And there's a simple way to solve that. We can simply change void up here, or we can simply change void up here to task. And now we have a way to track the state machine. Yep.
When should I do async void?
When you're working with event handlers. That's the only time. Right, so handling the exceptions. The exceptions are going to be swallowed by the tasks if you don't await them. So you need to verify that the task that runs the state machine actually run completely through without any exceptions. Because if you just call a method that has a task within it, and you don't verify that the task actually run completed and there was no exceptions, you're not going to get any exceptions thrown on your caller. And there's no way to actually catch the async void when there's an exception within async void. So in this case here, we changed the bolex async method signature to actually have the task instead of void. However, we still don't really get the exception thrown here, so this is called fire and forget. So we're just calling a method And that's going to set up a state machine, and there's going to be an exception within the state machine. It's going to set that on the task of the state machine, but we don't ask if it's completed and if there's no exceptions. There's a very simple way to actually verify that the method call and the task completed accordingly. We can simply await it. What this will do is that if there's an exception in here and we await that, that's going to throw the exception back on the caller. So we can catch that here and actually handle the exception in a correct manner. So don't do fire and forget. Another interesting topic to talk about when we talk about asynchronous programming is parallel programming. It's easy to confuse these two, and here's a definition of parallel programming. Parallel programming divides a problem into smaller pieces. So let's say that we have a certain amount of eggs to boil, and we have one pot to boil these eggs. Each pot fits 5 eggs, and we have 10 eggs to boil. So if we add another pot, that's going to divide the time that it takes to boil the eggs by 2. That's simple. However, asynchronous programming lets us delegate the work instead, and let us be notified when that's done. So there's a slight difference between these two. So here's an example how we can combine the parallel programming with the asynchronous programming. We can boil the eggs that we have in our pots, and then we can go ahead and do something else, or like clean the kitchen or something like that. And then when the egg timer goes off, we can come back to the stove and remove the eggs from there and eat them, or do whatever we like with them. And here's an illustration of how we can do that. So we simply run a task here with a parallel for loop inside it, which just illustrates a boiling time. Here's another interesting thing. How many in here have had deadlocking in their applications? All right. So think about this here. When we await something inside our methods, it's going to return the task that tracks the asynchronous work, which is the state machine. Now, if we call this method on our UI thread or on another thread, and we tell it to wait for that to complete, there's no way for it to actually notify us that the asynchronous work is done, because we're blocking the thread with our wait call. Here's an example of that. If we call MoveNext async, which returns a task, and this is called from the UI thread, and we do wait here, that's going to block the thread and wait for it to complete. But there's no way for the task that is running to notify the UI thread that it's done, because we're blocking the UI thread and waiting for the call to tell us that it's done. So it's very simple to solve this. We can use await instead. However, there's a big difference between just simply having the method call here with doing await here. Introducing await in front of this means that we need to mark the method as async. That means that the entire method body is going to be moved into the state machine, and we have a lot of more complex code generated for us. But this is a better way to do it. It's better to track this, add it to the state machine, and have that schedule a callback to us and tell us that it's done, rather than having the application deadlock. So let's actually take a look at how it might look like to work with Asyc. I'm going to show you the differences between Visual Studio 2012 and 2013, and show the debugger improvements that were made in the new Visual Studio 2013. However, to make the new changes work, you need to run Windows 8.1. So here I have a basic example application. It's a WPF application with 2 buttons. Let's see if I can.
Does anyone still use WPF?
No.
Yes.
I do forget. So I have 2 buttons here. One that boils 10 eggs and one that does something else. Let's just jump into the definition here and see what happens. So this method here simply invokes the egg boiler's MoveNext async, which we looked at before. And the other method here actually just throws an exception at us. And inside this here, we have the same code that we saw previously, except there's one more method call here, which is task.delay, and we're awaiting that as well. Let's add 2 breakpoints here and debug this application. And now when we're down here, you're going to see that I have a lot of code here. This is code from within the MS Core lib and from the presentation framework, and a lot of stuff that is generated by the compiler. And this is actually because I've turned on don't just show my code. So, however, there's not a lot of useful things here. If I scroll down at this moment, I can see that this actually originated from a button click. It's supposed to say button click here somewhere. Yeah. However, if I press F5 and come down to the second breakpoint, there's no way for us to actually see where we came from. We can see that this is from the main method, but these things here isn't really important to us when we were debugging this. The only thing that matters here is that we resumed an asynchronous method, and we have no idea who resumed it or where the call actually originated from. So let's jump into Visual Studio 2013. Looks fairly similar, but it's better. And I'm going to do the same thing here. I'm going to set a breakpoint here. I'm going to set a breakpoint down here. And debug this. And now when I click bold 10x here, we can clearly see that I came from bold 10x click, and I've turned off the external code here. And when I press F5 here, you'll see that we can still see where we came from. We can see the click event that triggered the asynchronous call. We can see that we arrived back from an asynchronous call, and there was a lot of external code in between, and we resumed the async call, and now we're at this line here. Notice this here, though. This is also a new window in Visual Studio 2013. We can see all the tasks that are currently running inside our applications. So I can see here that our task inside boil eggs click is currently awaiting this to finish, and this here is the task within the state machine. So you can see here, if I do this maybe, you'll see that it says the name of the generated state machine. So in this very small example, we can see that we have a much easier way to track where the asynchronous call came from. We have a better understanding of all the tasks that are currently running inside our application. And when we're working with really big business applications, this is going to be really helpful. Now let's look at something else interesting here. So the other button inside the application actually crashes the application. It throws an exception. The method signature for this one is simply return a task, but first throw the exception. So we don't need to return anything here. Now, if I copy this here and create an asynchronous version of this by simply adding the async keyword, I'm going to go back to this one here and change it to the asynchronous call, you're going to see that it actually swallows the exception and it's not traveled back to the UI. And if we jump into Reflector, you'll see that, let's change this to .NET 4.5. You'll see here that it just marks this as async. This looks fairly normal, but we have no idea why this isn't actually throwing an exception on the UI thread for us, because we know there's an exception within this. The problem is, if we look at this as a .NET 4.0 application, it generated a state machine for us and simply returns the task of the state machine. And if we go into this and take a look at what this state machine looks like, look what it does here. We have try, throw exception, catch it all. And it's going to set the exception on the builder, which in its turn is going to set this on the state machine thread task. Sorry. So there's a very simple way to solve this. As I said before, we can simply await the results. So if I mark this as async and await the throw call here, it's going to crash the application again. However, in this case, I can actually wrap this inside a try-catch block. And I can track the exception. I can store that, as you can see here. If I set a breakpoint down here, you'll see that it actually enters the, oops, actually, oops, to debug the application. So now I can catch the application here. I can catch the exception from the asynchronous call here. So that's very powerful. So there's a couple of other things that I like to just bring up that I don't really have time to go into. The first thing is the reactive extensions, or also called RX. Not sure if anyone here has worked with reactive extensions. Their definition of RX is it's a library to compose asynchronous and event-based programming using observable collections and linked-based query-style operators. And from what I've seen, the examples, I haven't worked with it that much at all. But from the examples that I've seen, it looks really nice. And from everyone that's been working with it, they say it's really good. The second thing is immutable collections. So immutable collections are introduced by the ECL team at Microsoft, I think it is. And it's available on NuGet. So we can install these immutable collections inside our applications today and use them. And the good thing about this is that when we have immutable collections or immutable types, we don't have to worry about anyone else stepping on our toes and changing the layout of this collection or the layout of the object or whatever is inside the object or collection. So imagine that we have a person collection, and we need to go over all the persons in the person collection. Then if someone else is from outside changes this frequently, then we can't be sure that everything is as is when we've started and ended. So it's simply to avoid someone stepping on your toes and be sure that the data is consistent during the time of the execution. If you don't have any questions, I want to thank you for listening to me, and you have my contact details here. If you have any questions about IKEA, I can take them as well.
It's meatballs real. It's meatballs real.
The meatballs?
Real?
Yeah, they're real. Yeah. But you know, the ones on IKEA here, they're actually produced in Australia. And the meatballs everywhere else in the world are produced on the same place. But Australia don't really want the meatballs from outside, so they do them themselves.
We don't want horse meatballs.
Yeah. Have you tasted them? They're much better. All right, no questions?
All right, let's take a break and eat some pizza then. Thanks, guys.